I am in my costume today as a presentable human being. I'm Galen George, Siemens Energy. I am one of the OEMs, by the way. But I deal in digital software. So I'm not a gas turbine mechanical guy by any means. I am currently the Director of Business Development and Digital Sales for Siemens Energy. Living in Alpharetta, Georgia, which is a suburb of Atlanta. I've been with Siemens for 28 plus years now, believe it or not. I don't look as old as I actually am. I've been in the industry for 40 years. So I have a lot of hard experience in the industry. And I've been in electrical and software most of my career. What I want to talk to you guys today about is using digital AI and software to improve the flexibility and the performance of our assets, focusing combined cycles. But in the area of market flexibility and dealing with the transition we're going through right now with plants that were built to be base load that find themselves in a market, an ever-increasing market, where they're no longer operating that way. The disclaimer has to be in here because you guys are going to get print copies of this, so the legal always makes me put these disclaimers in. But what's happening to us today? Historical operations of all of our assets, but especially some of these assets that were built in the first half of the century, the first decade in the century and the second, the thought was coal will go away, all these plants will be built to run base load, and that hasn't happened. We even have a bit of a nuclear renaissance right now, so that's even more putting impacts on how these plants operate in a way they were not originally designed to operate. You add all the renewable portfolio standards by states, and the fact that we can never seem to have an actual federal energy policy. We flip every 4 to 8 years on what we want to do. What's happening in all of the markets in all the regions, even the regulated ones, is that these combined cycles are being asked to operate in a far more flexible manner than they originally intended to be operating in. That problem leaves some great opportunities. In some markets, you can make extra money. In some of the open markets, by being more flexible and addressing market flexibility as well as operational flexibility. And I get into some of that. So what do I mean when I say flexibility? Particularly right now, especially in this part of the world and down in Texas, starting up, shutting down faster, getting into and out of the market as quickly as you can for at least cost as you can, being able to provide expanded ancillary services like air regulation and frequency support in Texas. We didn't think we had to worry about things like that in this country, but we do now because of what's happening with renewables. Reducing your minimum loads, if you operate in CAISO and the power is actually negative priced at night, you either don't want to be online or you want to be online for as little as you can possibly lose overnight. And then providing some type of frequency support and spinning reserves. All of this has to be done within the emissions limits that you're permitted to run and operate under. So the best way to explain some of these solutions is to talk about an actual project, I think, instead of theoretical information. So we actually execute a project with a customer who, and I use this example for a specific reason. If you notice, none of the equipment on this plant came from Siemens Energy. Obviously, we've done many projects of our own equipment, but we have this impression that even in the digital software world, Siemens focuses on Siemens only. That's not the case. We do as many projects with other people's equipment as we do with ours. This is a 2x2-on-1 combined cycle, 7 FAs down in Oklahoma, actually. At the time I put this presentation together, we didn't have permission to use the name. We do now. The plant is called Oneida. It's in Broken Arrow, Oklahoma. It operates both in ERCOT and Southwest Power Pool, so it can trade its power both ways. In the Southwest Power Pool, it's one of the few merchant plants operating in that market. In ERCOT, of course, it's competing for every megawatt hour. As part of this project, we upgraded the plant DCS. They had an older plant DCS that was put in like 2001. And they worked with GE to upgrade their Mark 6 control systems. They did a new HMI upgrade, And a part of that, they improved some of the communication capability of their GE systems. So we didn't actually replace the GE systems. We communicated to them and worked with them. When looking at the Southwest Power Pool, I modeled it in the Southwest Power Pool because ERCOT is a very aggressive market. So I wanted to show an example of one of the more conservative markets and the opportunities there. But even in Southwest Power Pool, ancillary service markets are becoming more and more of an impact on commercial operation. So there's opportunities, even in a basically regulated market, to make money on the marketplace by providing ancillary services and improving your position in ancillary services. It also, and it's hard to model, in Southwest Power Pool, you may become more, based on where you are, you may become more attractive to the market simply because you can provide more area regulation, AGC, or better services, higher ramp rates and stuff like that. So it's kind of hard to model where you change in the marketplace from a dispatch standpoint, but they do see your plan as more attractive, also in ERCOT as well. So what we did with this customer as part of this DCS replacement is we use software and AI to improve their startups in two ways. One, to shorten the times, and this is warm, cold, and hot, and reduce, more importantly, reduce their hurdle costs to get into and out of the market. So improving their startup times does two things. One, time to market is quicker. It reduces the risk of you not making it on the hour. In ERCOT, if you miss the hour start when you're supposed to dispatch on the hour, you may lose your entire day. As Southwest Power Pool, you may get penalized. They'll still dispatch you, but they'll penalize you with a fine. So those two benefits are there. Also, reducing your hurdle costs means you're cheaper to get into and out of the market depending on how you model your plant. Some customers will throw their startup costs or their hurdle costs into their energy price, which artificially increases their dispatch price. Some customers will actually market a hurdle cost. They'll tell the dispatcher how much they have to pay them to get into and out of the market. And that may make your plant less attractive to get there. So if you could reduce those costs, you become more attractive to the region that you're dispatched in, and you can increase your profits as well while you're in their market. We use different approaches. One is it's a little bit more automation. We have the capability of programming a system to be a single push button to start, and the operators don't have to do anything. We have found no customers in the United States that finds that an attractive way to operate. So what we do is we don't fully automate the plant, but we automate it such that the operators are very comfortable starting the plant. They have, instead of 50 steps to start the plant, they really only have 5 or 6 to do it. And then we give them the graphics I'll show you to do that effectively. We do have to change some of the control structures. One of the flaws in the traditional controls is you can't tune a system to operate steady state optimally and in a transient at the same time. So you have to have adaptive controls that understand the differences in the control structures between those two. Using models and then AI give you that capability. And then we use stress evaluation because if you're going to be moving the unit faster, you have to worry about the stresses you put on the equipment. Nobody wants to change your operational profile, as advantageous as it may be, but then have to take the units down more often and increase your maintenance costs, because that's not worth it at all. So the first thing I talked about, we automate the plant more, but make it comfortable for the operators to do so. If the operators are not comfortable, my experience in any power plant, if you don't make the operators comfortable, they won't use it. They'll turn it off, whatever system you have, and the project will be a failure before it even starts. We produce graphics that are very easy for the customer to use. Imagine having a first out and a startup ready graphic for your entire plant, not just your gas turbine, not just your HRSGs and water steam cycle and steam turbine. We've always been great about providing that for the gas turbines and the steam turbines, but the rest of the plant is where the real work has to be done. So imagine having, for your operators, a ready-to-start graphic for everything, and then one that sequences them through the startup, tells them where everything is ready, and if it finds a problem, it finds it before it becomes a problem, alerts them, it gives them an indicator on how to fix it and address it, and if they can, you just move on. So it doesn't become an obstacle for the startup routine. So a combination of automation and model-based controls and graphical representation, so that if the mechanical plant does have a problem representing a stop for the start, it addresses it proactively, lets the operators know what they have to do. They can address it before the startup, it interrupts the startup coming in. Operators are very, very, very comfortable with this. That was a feature they liked the most, believe it or not. Just a breakdown of the kind of areas we look at. We do look at the combustion turbines. We use a computer-based AI model to guide, and I'll explain that later, to guide the startup of the combustion turbine and the loading. If you get a faster GT ramp, you lose less fuel coming up, but you still have to worry about your stresses. And obviously, if it's our gas turbines, there's things we can do to further improve the ramp rate on those gas turbines. On the HRSG and the water steam cycle, we model the stresses on the boilers. We use routines for bypass and charging, and we get the unit up through the cycle faster by changing some of the way they actually start the plant. And then on the steam turbine, we have tricks and trades there, using stress calculation, using bypasses better than they're being used currently, or designed to be used currently, to get the steam turbines on earlier and faster in the process. When you put it all together and you coordinate it, you have a much faster startup. So one of the keys to doing this, and we have the privilege, Siemens Energy has a bilateral agreement with just about every HRSG manufacturer out there. Two reasons. One, we're a big customer. We buy a lot of HRSGs to build turnkey power plants. But all of these manufacturers use our Benson technology, their once-through technology, to model their manufacturing. So as that bilateral agreement, they get to use our models and our simulators in Europe, in Germany. We get the material properties. Without the material properties, we cannot do this calculation. So we call this the predictive load margin computer. And what it does, it models the stresses on the HRSG from the exit of the gas turbine through the economizer. And it not just models in real time what stresses the equipment is going through, it predicts based on loading of heat into the HRSG, the rate of change of heat into the HRSG, all the thick wall components, what stresses will happen in the future on a first order time delay based on what energy you're putting into the gas turbine now. I equate this, how many people have done go-kart racing? You know, the best way, the fastest way on the track is not, and I do it all the time, so I know I'm not an expert at it by any means. The nature is to, you know, hit the gas on the straightaways and then skid through the corners. It's the same thing here. It's the worst way to get around the track. It's fun, but it's the worst way to get around the track. The best way to get around the track is to calculate the appropriate speed during the straights so you can make it around the corners as quickly as possible. The net result is you make it around the track in the quickest time. That's a very simplified version of what this is doing as well. It's loading the gas turbines for not just the stresses that are on the HRSG thick wall components, but what they will have when they go through the criticals. And every mechanical piece of equipment has criticals. So it may actually load the gas turbines slightly slower in certain periods of time when you're getting the gas turbines up online, but the net result after everything is, when the gas turbines start and the steam turbines coupling, is that you've managed the stresses. You can actually load the unit up to the limited stresses on the thick wall components of the plant without ever causing a stress. We've actually run historical data through this model after some of the plants we worked on and found out that many times they were, especially on cold starts, they actually were putting thermal stresses on the equipment. And you know, we give them this information after the fact. We do similar things for the steam turbine, how we couple the steam turbine and bring it in. And when you put it all together, you get a very effective startup. The other benefit is that it's repeatable with the automation. So if a warm start takes 45 minutes, it's going to take 45 minutes all the time. And so customers who are worried about hitting the top of the hour, what they'll do now is start 30 minutes early and sit around waiting to be dispatched while burning fuel. Now you don't have to do that. You can count on your startup being what it says it's supposed to be, and start up when you need it to start and not have to waste fuel waiting to be dispatched. So at the end of the day, when we finished this project, we did this project, the first power block was in 2018. The second power block was the end of 2019, just to get it ahead of COVID. And the results, like I said, we modernized the DCS. We put in some advanced controls. We did the predictive load margin computer. We also optimized their cooling tower for some heat rate benefits. And there's something else we put in here I'll talk about in a minute, improving their area regulation capabilities on AGC. But at the end of the day, what paid for the project, we reduced their starts on 2-on-1 by 50%, and we had to do both 2-on-1 and 1-on-1 because that's how they dispatch the plant sometimes. They didn't always dispatch the entire power block. They would do it 1-on-1 with the additive. So we had to do both, 2-on-1, 50%, 1-on-1, 45%. Average savings of costs, their hurdle cost in. Now, they also paid for electricity, so they had demand charge costs as well as fuel cost. Overall, the cost was reduced by 50%. We also integrate the HMI so that we have the capability to pull in third-party systems that are web-enabled so that you don't need those consoles. You actually operate the GE system from within the Siemens Energy DCS. So we updated their console. They spent a lot of money on a really nice central console that moved up and down. It had disco lights at the end. I call it the disc. All they're missing is the little ball in the ceiling that really makes this controller fancy. We also put in some thermal performance monitoring because they had no idea what the heat rate was, believe it or not, throughout the cycle. They knew what design heat rate was at base load, but a plant like this never runs at base load, or rarely runs at base load. So off of base load, they had no idea what the heat rate was. So they really didn't know how to bid their energy price. They were significantly underbidding their energy price. The way we execute this, I talked about a little bit, is, it's not a one-size-fits-all. I wish it was a one-size-fits-all program. It's customized engineering for every different plant. And even the 2 power blocks on this facility, same equipment designed to be identical, didn't operate identically. So we have to engineer in layers. I talked about the automation first. We use application and dynamic adjustments, advanced controls, model-based, and then we put in AI for the optimization overall and the master control. The other thing about our system, and I was one of the designers on this platform, my hatred for optimizers in the past is everything had to be coded. You had to have a programming engineer to be able to manipulate and use it. When we designed ours, I wanted to not have to do that because I'm not a programmer by any means. So I wanted to be done like a function block type of logic like you do in any DCS. So we designed a system to operate just like the control system that it sits within. Obviously, we use our own to do that. So you can engineer this product. You don't have to program it in the true sense of the word. All the previous optimizers I worked with, or I had the less than privilege of working with, you had to be a programmer to really implement them. I talked about it. It's not a one-size-fits-all, so we don't just go in and apply standard software and hope for the best, turn on the AI and hope for the best. We actually do plant assessments. We do studies. We take test data. We run it through a simulator that we have it back in the office, and that tells us what we can actually achieve or what we can estimate to achieve based on that data. We present what we're going to do and what we think the results will be to the customer, and then based on that, they'll move forward with what they want to do. This is just an example of what in the graphs we showed them, where before and after what we would do to improve the startups, because not every customer wants us to do everything we think is best to improve the starts. Usually, 90% of us, they're aligned because they want the results. Like I said, so it's a heavily engineered solution. It's customized for every plant. And this was the customer actually gave a co-paper with me at a conference meeting a year later when we reopened, and this was from them. They, as a merchant plant, they be able to compete in that market now much better than they did before. The previous owner was LS Power. That's who did the project. They successfully sold this plant a year later and made a mint because of the capabilities they had in both markets after the fact. The other thing we did with them is we have a solution we call Flex Assist. And what it does is automates your duct firing, your supplemental firing into your AGC without having the operators to interfere with it at all. So they actually increased the dispatchable range by 200 megawatts per power block. In ERCOT, they actually pay you for that. You can make additional dollars per kilowatt or megawatt hour by having extended AGC range. Southwest Power Pool doesn't pay for that, but it makes me more attractive to the dispatcher, to the RTO. And with that, any questions? I wanted to keep it short and sweet. And by the way, no mechanical changes had to be made to the plant. This was all controls and AI.
I'll start off with a question for you, Galen. Did you add heat blankets to the steam turbine or sparging steam on the?
No, did not.
Interesting.
The only change we made to the steam turbine was logically and procedurally where we brought it in earlier in the startup cycle. We didn't have to wait till all the inlet steam was at perfect temperatures and pressures. We actually controlled the enthalpy of the steam so we could bring the steam turbine in earlier. We also rolled off on the IP steam. Yeah, with the D11s you could do that. Ironically, we could do more with the D11 than we could do with our own. Don't tell anybody in Siemens I said that, please. So yeah, we didn't do blankets or anything. Now these gas turbines had LCIs. We call them SFCs. They're static starts. We did make some improvements on the static start capability that brought the gas turbine itself up quicker. The other thing that I'm big on the steam turbine is how you control the drains, not just on the steam turbine, but on the HRSG drains. If you do them based on the thermal balance cycle, not a routine, or let's face it, most of them aren't automated in any of these plants. They're not automated. So what happens is the operators leave them wide open until they get way past the steam conditions, and then they start closing them, or they just close them all at once. They don't think about the optimal closing time for the startup procedure. So by using a model of the thermal cycle to close your HRSG and your steam turbine drains, you bring the whole unit up faster as well.
And what about shutdown purge credit?
We didn't increase the purge credit, but we did reduce the shutdown time on the gas turbines. So an indirect effect is that you get that extra time in purge credits because you run more air through it.
Okay, thank you. Any other questions over here?
Did you all find any unintended consequences from this, like increased maintenance cost or
No.
premature failure?
That's one thing that we say, as an OEM, we have LTPs just like, or LTSAs. We call them different things, but they're the same thing. We have service contracts. So, and many of them include the steam turbine. We have O&M contracts where we have guarantees availabilities on the entire plant, including their HRSGs. So my mechanical department would have never allowed us to introduce anything that would cause more thermal cycling or more. The one area you have to be careful on, though, is that you have to have good water chemistry. Water chemistry has to be good. That could cause other issues, unintended issues. But as long as you have that, there's no thermal cycling. In fact, on one of our OEM plants where we did this, we found that we were stressing the equipment less than they were when they were operating before. On our steam turbines, we have the thermal stress calculators, so you can actually make the decision to use a little bit of life out of the steam turbine and start even faster. So we do have even better results on some of our own equipment because we give the operator that capability to determine if you really want to get in the market quick, you can take a little life out of the steam turbine, and it calculates what that life would be.
How were the emissions affected on the faster startup? Or were they
So on emissions, you get startup emissions, you get operating emissions. Actually, especially for this plant, the way their contract was structured, because they have startup emissions limitations and they have operating emissions limitations, we actually reduced their emissions because it's a total. By starting faster, you actually reduce the emissions on the startup for the gas turbine. That's when you're producing most of your CO. After you got to load your controlled your CO. NOx was not a problem. We came through. They didn't reduce their NOx because that was part per minute, but they didn't increase their NOx either. Now, having said that, that could be based on how the contract's structured, and that may be one of the limitations that we have to take into consideration when we do that plan assessment up front. That's a great question. That's exactly the type of things we look at up front when we do the assessment, what we have to do and what we can do.
Any other questions? Going once, going twice. Galen, appreciate it. Great job. Thank you.
All right. Thanks a lot.